Here we are going to discuss some problems related with DC generator portions that includes generated EMF, losses found in DC generators and efficiencies. So we can solve the first question. A 100 kilowatt 250 volt DC 6 pole shunt generator runs at 1000 rpm when delivering full load. The armature has 534 lap connected conductors. Full load copper loss is 0.64 kilowatt. The total brush drop is 1 volt and determine the flux per pole. Neglect shunt current. Normal case in shunt generators we neglect shunt currents. Okay. We can solve this problem. First, we can write what are the given data found in this problem. First, 10 kilowatt, that is the output power. So, power output. GD given data. Power output is 10 kilowatt, that is 10 into 10 raised to 3 watts. And 250 volt terminal voltage is 250 volt, and pole number of pole, that is 6 pole. So P is the number of pole, that is equal to 6. Shunt generator runs at 1000 rpm, so speed is 1000 rpm when delivering full load. The armature has 534 lap connected conductors. Okay, so the number of conductors, total number of conductors Z is equal to 534. Okay, and it is given that it is lap connected windings. So in lap connected windings, number of parallel path A is equal to number of poles, that is 6. For wave windings, number of parallel path is always 2 for simplex windings. So it is given here. It is lap connected windings. So full load copper loss is 0.64 kilowatt. So full load copper loss, that means it is armature copper loss or armature copper loss, that is equal to 0.64 kilowatt, that is 0.6 into 10 raised to 3, that much of watts. Okay, then total brush drop is 1 volt, so VB is 1 volt, and we need to find the flux per pole. Neglect the shunt currents. Okay, these are the major data which are given in the problem. Okay, we know that flux per pole, we can find the flux per pole from the generated EMF equation. We know that Eg is the EMF generated in the generator. Eg is equal to phi Z n by 60 into P by A. This is the equation for generated EMF. And also we know that Eg is equal to terminal voltage plus voltage drop across the shunt field plus voltage drop across the armature resistance or armature windings plus brush voltage drop. In the case of shunt generators, we neglect the current through the shunt field windings. So we need only the voltage drop across the armature winding, that is IARA plus brush voltage drop. Okay, this is the equation for generated EMF in DC generators. So in the first equation, Eg is equal to phi Zn by 60 into P by A. We know that we need to find the value of flux. Z is given, N is given, P is given, A is given. But the unknown quantities are Eg and phi. So phi is the parameter that which we need to find out from the question. So in order to find out the value of this flux, first we should understand or we should calculate the value of Eg. For that we can use this formula. Eg is equal to V plus Ia Ra plus Vb. We know that in this case armature current shunt field current is neglected, so that armature current Ia, we can calculate the value of Ia. Ia is equal to I is equal to, because we are neglecting the shunt field losses, power divided by voltage. So we will get power is 10 kW, that is 10 into 10 raised to 3 divided by terminal voltage is 250. So we can calculate this value and we will get the value as 40 ampere. This is the armature current for this question. Okay. Armature current is given. So we need to find the value of this Ra. Ra is unknown. But we know that full load copper loss is already given. That is 0.64 kW. Full load copper loss, we can calculate the full load copper loss from Ia square Ra, that is 0.64 into 10 raised to 3. From here we will get Ra is equal to 0.64 into 10 raised to 3 divided by Ia square. So already Ia is 40, so 40 square. After calculating we will get Ra is equal to, after calculating we will get Ra is equal to 0.4 ohm. That is the value of Ra. Ra is nothing but armature resistance. So we can use this Ia and Ra to find out the generated voltage. So we can write Eg is equal to V. V is 250 volt, V plus Ia into Ra. Ia is 40 into Ra is 0.4 plus Vb. Voltage drop across the brush, that is 1 volt. And finally we will get the generated voltage as 250 plus 16 plus this 1 volt. We will get 267. Okay, 267 volt. That is the generated EMF. So by using this equation we will get the value of flux. From this equation we can write the equation for flux. Phi is equal to Eg divided by Z into N into P, and 60 into A. So by substituting the value, Eg is nothing but 267 into 60. A and P are same. 60 into value of P is 6 divided by value of Z is 534 into N is 1000 into P is 6. So after calculating we will get 0.03, that much of Weber, that is equal to 30 milliweber. That is the value for flux. So we will get the value of flux from this equation. Eg is equal to 5 third np by 60 into p by a. If Eg is not given, then we can use this formula to find out Eg. Then other terms are, if other terms are already given, then we can solve this problem by this method. Okay. Now let us discuss about one another problem. This is that problem. It reads as a shunt generator delivers 195 ampere at terminal potential of 250 volt. The armature resistance and shunt field resistance are 0.02 ohm and 50 ohm respectively. The iron and frictional losses equal to 950 watts. Then find A. EMF generated, B. Copper losses, C. Output of the prime mover, and D. Commercial, mechanical and electrical efficiencies. So we need to find these these four parameters. So first of all, we can write what are the major datas which is given in this problem. Okay, we can write it as given datas. Given datas. What are the given datas? Shunt current delivers 195 ampere at terminal. So it is clear that 195 ampere is the load current, that is IL. Terminal load current, that is 195 ampere. Terminal potential difference of 250. That means terminal voltage, that is V is equal to 250 volt. The armature resistance and shunt field resistance are 0.02 and 50 ohm respectively. So RA is given as 0.02 ohm and shunt field resistance, that is RSH, that is given as 50 ohm. Okay, the iron and frictional losses are 950 watts. Iron and frictional losses. So iron plus frictional losses, that can collectively call as stray losses. Stray losses, which is given as 950 watts. Then we need to find EMF generated first. Okay, these are the major datas which is given in this problem. So we can calculate, based on these datas we can calculate EMF generated. Okay, we need to find EMF generated. In order to find the generated EMF, we need to know the terminal voltage, and since it is shunt generator, we neglect the current through the shunt field. So we need to know the voltage drop across the armature field windings, and we can neglect the brush drop, otherwise we can choose it as 1 volt nearly. So here we will consider the generated EMF, that is Eg. We need to calculate, that is Eg is equal to V plus IARA in this case. So V is already given in the problem, and we need to calculate IA. For that, from these datas, first we can calculate current through the shunt field, because armature current Ia is the sum of shunt field current with the load current. So we can first calculate current through the shunt field winding, that is ISH. ISH is nothing but 250 divided by 50, V divided by R, RSH. Okay, voltage across the terminal divided by RSH, and we will get 250 divided by 50, that is 5 ampere. So 5 ampere is the shunt field current. From this we can calculate IA is equal to IL plus ISH. So IL is already given, that is 195 plus ISH 5 ampere. So we will get 200 ampere as the armature current. Okay. So directly we will get EG is equal to V plus IAR. V is 250 plus IA into RA. IA is 200 and RA is 0.02. 0.02 and we will get 250 plus 4, that is 254 is the, that much of voltage is the generated voltage. So first part completed. EMF generated is 254 volt. Okay, then we can go to the next question, that is we need to find out the copper losses. Copper losses, we know that copper losses, in this case copper losses includes both armature copper loss and shunt field copper loss. Okay, second question we need copper loss. Okay, copper loss includes armature copper loss plus shunt field copper losses. Okay, so first we can calculate armature copper loss. Armature copper loss, that is Ia square Ra. Already we know the value of Ia, that is 200 square. 200 square into Ra is given, that is 0.02 ohm. After calculation we will get Ia square Ra 800 watts. 800 watts is the armature copper loss. Okay, next we need to calculate shunt field copper losses. Okay, shunt field copper losses. We can calculate the shunt field copper losses by the product of terminal voltage and shunt field current by using this equation. Okay, shunt field copper loss, every losses are the power loss. So power P is equal to V into I. For finding the shunt field copper losses we use this equation, and for armature copper losses I square R. This is the equation that we are using, and we must remember that every losses are power losses. Okay, so shunt field copper losses can be V into ISH, and V is already given, that is 250, and ISH, what is ISH, that is 5 ampere. Already We calculated for the first part, that is IA. So 250 into 5 ampere, and we will get 1250 watts. So this is the shunt field copper loss. So we can calculate total copper losses. Okay, total copper losses is equal to armature copper losses plus shunt field copper losses. Okay, armature copper loss is 800 watts. So 800 plus shunt field copper loss is 1250. So we will get the total losses as 20 50 watts, that is. So this is the total copper losses. So we completed the second part, copper losses. And the third case, that is, say, output of the prime mover. That is the third case, output of the prime mover. We know that output of the prime mover is nothing but the input of the generator. Okay, we know that the prime mover is directly coupled to the generator. So the prime output of the prime mover is the exact input of the generator. So we can calculate the input of the generator. So output of the prime mover is means input of the generator. Okay, and we know that input of the generator is nothing but output plus losses. Input is nothing but output plus losses. Okay, and we can calculate output by using the equation, that is load current is load current IL is already given 195, and terminal voltage is given, that is 250. By using these two things we can calculate output. So we can written as output is equal to, what is 195 into 250. Okay, output is equal to 195 into 250 is the output. And losses, what are the losses? Already we know that total copper loss is nothing but 2050 watts. So 2050 is the total copper loss, and in the question which is already given the stray losses, that is 950. So we can add these losses with the total copper losses, 950. So output is 195 into 250, and losses is total copper losses plus stray losses or and frictional losses, and we will get 48750 plus total losses is 3000. So the total input is this is the total input. So this is the output of the prime mover. Okay, so we completed the third parts also, that is output of the prime mover. And the last part, that is, we need to calculate the commercial, mechanical and electrical efficiencies. And before going to learn to calculate these efficiencies, we know that for the machine, this is the mechanical input which is given. Then some losses will occur here, that is iron and frictional losses. That is, collectively we can call it as stray losses. And we will get electrical power generated after these losses. Electrical power will generate in the armature or develop. And some losses will occur here, that is copper losses. Copper losses occurs in armature windings, and also copper losses will be occur in the field windings also, armature and field windings. So, and after this we will get electrical power output. So when we give the mechanical input to the generator, due to iron and frictional losses, some power will get wasted and electrical power will get generated in the armature. We can reduce these losses. We can subtract these losses from the input, then we will get the electrical power. And after this copper losses, finally we will get the electrical power. And before going to find out the efficiency, mechanical, electrical and commercial efficiencies, we must understand these things. And already we discussed about this in the previous lectures. Okay, you can check it. So based on these concepts, we can solve this. That is, first we can calculate the mechanical efficiency. Mechanical efficiency is nothing but the ratio between electrical power developed or generated divided by mechanical input. That is nothing but output by input. Okay. So mechanical efficiency is equal to the ratio of electrical power developed divided by mechanical input that is given to the generator, or output of the prime mover. Output of prime mover. So electrical power developed. Already we know that electrical input that is given to the generator is 51,750 watts. 51,750 is the 51,750, that is the input that is already given as the input to the generator. And some losses will occur here, that is iron and frictional losses. Okay, here it is already 51,750 is already given here, and due to this iron and frictional losses, that is 950, we will get a reduced power at here, or we will get means generator will generate that much of power, minus 950 and 5800. Okay, divided by the output of the prime mover, that is the input which is already given, 51,750. 51,750 . into 100, and we will get the efficiency as 98.2 percentage. That is the mechanical efficiency for the given machine. And next we can find out the electrical efficiency. Electrical efficiency, based on this power flow diagram, we can say that electrical efficiency is nothing but the ratio of electrical power at the output divided by the electrical power generated. Okay, here we need to subtract the electrical power generated. Okay, from this we can subtract the copper losses. So here it is already 5800, and total copper losses is, we calculated that 2050 watts. So copper losses is 2050. That is the copper losses. And based on this, we can calculate the electrical efficiency. So electrical efficiency is the ratio of electrical power at the output divided by electrical power generated. Generated electrical power is 50 80, okay, 800. Electrical power at the output is nothing but the difference between the electrical power generated and the copper losses. Okay, we need to subtract this electrical power generated here. We need to subtract from this value copper losses, we can subtract. So 50 800 minus 2050, and we will get it as 48,750 divided by 50 800 into 100, that is 95 percentage is the efficiency. From this stage efficiency is decreasing. Okay, and we can calculate the overall efficiency or commercial efficiency. Overall or commercial efficiency is nothing but electrical power at the outputs divided by input given to the generator, or output of the prime mover. Okay, electrical power at the output, that is 48,750 divided by input which is already given, that is 51,750 here. So we can divide this with 51,750, and finally we will get it as 94 percentage. Efficiency is decreasing. Mechanical efficiency is the maximum efficiency. Okay, so in this ways we can calculate the problems. Okay, thank you.